Okay, this is going to be the video for the third day, and this will wrap up the notes for chapter 18. And we will summarize what we've talked about so far, and then we'll add on a couple little odds and ends, and then we're going to do the first two real problems in the practice packet. Okay, so this third day, let's just review where we've been at. We've talked about two separate cases here: numerical variables, which are sometimes called quantitative, and categorical variables, which are sometimes called qualitative. In numerical value, you have some sort of numerical data here, like, say, the heights of adults in the United States. Categorical is something like yes or no. Do people have blue eyes or do they not have blue eyes? Something like that. So the population has um, that's what we're trying to generalize to, right? And anything we measure about that we call a parameter, right? Usually Greek letters. In the numerical case, we use mu for the mean and sigma for the standard deviation. This proportions case is the only one that breaks that rule. We use p for the proportion for the parameter population. But we don't usually work with the population. We usually work with a sample. So we take a sample of all these data values, x, or a sample which will include some no's and some yeses here, right? Sample size is called n. All right. And then if we analyze the sample in the numerical case, since that's numerical, we could plug that in a calculator and do one variable stats and get the mean and the standard deviation. But these are called statistics, so we use English letters, x bar for the mean and s for the standard deviation. Over here, we would have a percentage of yes in the sample, right? And so we have to have a different symbol, so we use p hat for the statistic, right? Both of these are estimates of their parameters above, right? So there's two parameters over here. There's the mean and the standard deviation estimated by x bar and s, and there's one set of statistics and parameter over here, just the percentage of yes, p here and p hat. But whenever I take many samples, then I can measure the measure of center one, the mean, and every one of the samples will have a different mean, right? That's called natural sampling variation or random sampling variation, right? And we expect that to vary, right? Same thing over here in the yes no case, right? If I look at the percentage of yeses, I'll get a different p hat value for each sample. It varies from sample to sample. But because both of these cases, even in this case where we yes and no, these p's are percentages, right? Or proportions like 0.3, 0.4, 0.57, something like that. Then that means there's a distribution at this level too. This is called the sampling distribution level. This is called a sampling distribution of sample means, because it shows how sample means vary. And this is called a sampling distribution of sample proportions, because it shows how sample proportions vary. And technically it represents the graph should include all possible samples you could take from the population. All right, because those have a shape, they have a mean and standard deviation. So this is called the mean of means and the standard deviation of means. And this is called the mean of the proportions and the standard deviation of the proportions. So those are the symbols. Okay. All right. So whenever we have parameters are some sort of unknown constant that we usually don't know at the beginning of the problem. Okay. Statistics are random variables which vary from sample to sample and are estimates. So we're using the statistics to infer things about the currently unknown parameters usually. Okay. Occasionally we kind of work in fantasy land where we tell you the population values and the sample, and we want to figure out things. But in the real world, mostly we know this and we're inferring things about this from what we can gather from the sample, because we usually don't have these values. If we had the population, we wouldn't bother to take a sample. All right. Okay, so where are the middle of these sampling distribution means? Well, the middle always matches the population value. And that's true for both the mean and the mean here. The mean matches the mean of the population, and the mean of all these p hats will align itself with whatever the percentage is yes in the population. Okay, there's different formulas for the standard deviation. For the standard deviation over here, it's equal to the standard deviation of the population divided by the square root of n, right? Over here, I'm going to write this a little more cleanly as pq over n, right? This is weird. This standard deviation does not depend, there is no standard deviation up here, right? So it has to just be based on the p. So technically it's going to be the p value from the population times 1 minus p over the square root of over n, right? And really both of these things end up being, I mean, you could write this as the square root of pq over the square root of n. So both of these vary as the square root of n on the bottom, okay? All right, so the shape down there at the sampling distribution model level is normal or approximately normal as long as certain conditions are met. For the numerical case, it's given by the central limit theorem that the sample size has to be at least 30. That means it'll be normal no matter how crazy the shape is of the population. But if you're sampling out of a normal population, you can get by with less if the population is closer to normal, okay? For the yes/no variables, the requirement is that NP and NQ have to be at least 10 so that the normal approximation to binomial applies. All right? All right, that's a summary of what we've seen so far. So a couple of new things. So in inferential statistics, because so much stuff rides on the fact that the sampling distribution model has to be normal, we have a few important conditions, and I will add on a couple of other things as well. So the first thing is we want to always have a sampling distribution model that's normal, so we have a sample size condition. In the case of means or numerical variables, n has to be at least 30, or you have to be sampling from some closer to normal population, right? In the case of proportions, NP is at least 10, NQ is at least 10, okay? The second criteria is that your sample has to always be representative of the population. So you have to have a simple random sample, or you have to believe that it's representative of the population, right? In other words, we need to have an unbiased sample, right? No matter what we do with the analysis, if the sample is a bad if it's a poor sample, there's nothing we can do in the analysis to get rid of that fact. Okay, and then the third thing is that there's some things that we're going to come up with later that require independence between the samples. So to make sure that we can assume that the chances are all staying the same, we're going to have another limit on the sample size. Although we want it to be large so that this is normal, we don't want it to be too large. So we're going to require that we never sample more than 10% of the population. That's known as the 10% condition. In the case of means, it's mainly because if you have, let's say, a skewed population like this, and you were going to sample something, let's say I had a sample of 20, which is a nice big sample, or maybe 40, right? So I take 40, right? And I take that and I get a mean here, right? If I took a different sample of 40, I would get a mean, and they would all be kind of close to the actual mean here, right? So this can be a nice mean. The problem is, if you sample like the whole population, then your sample ends up becoming shaped like the population. So the reason why we don't want this to get too high is we don't want it to start replicating, we don't want the sample to start replicating the shape of the population. Okay, in the case over here, we want everything to apply as a binomial, and one of the requirements for binomial was the trials were independent. So to keep the probability of yes staying approximately constant, we can't sample more than 10% of the population. So in both the numerical and these cases, we have the same requirement. We want the sample size to be big enough, right, so that we have normal, right, but we want it to be small enough that we're not sampling too much, right? So there's kind of a sweet spot. And usually it's just you want to be a little over 30, something like that. All right. Okay, so what about this? Let me go back to this page for a second. Okay, it's true that the standard deviation down here depends upon the population standard deviation, and over here it depends on knowing the population p. But we just said we usually don't know this, right? We usually don't know these things up here. This is hidden to us. We don't know this, and we're only working with our sample. So what happens? How do we calculate this if we don't have the values? Well, what we do is we use the next best thing. We use whatever values we have that are estimates. So instead of using the sigma, we use the S, which is approximating the sigma. And instead of using the P, we use the P hat from the sample because that's an approximate value. Okay, whenever we do that, when we don't know the true population values and we use S instead of sigma, or we use p hat instead of p, then instead of calling this the standard deviation, we call it the standard error. Okay, so there's a new name for it if we're using an estimate from the sample. So instead of calling it sigma, we use the symbol SE for standard error. So instead of sigma x bar or sigma p hat, we use SE. Okay, so this is often just written SE p hat or SE x bar. And yeah, go ahead and laugh about the fact that that spells out the word sex. Get it out of your system. Yep, that's the standard way to write the standard error of x bars. Okay. So very frequently, we're actually finding standard errors instead of standard deviations. It's a subtlety, but I want to just give you the details now so that when it comes up and becomes more important later, we'll understand. One last thing before we look at some problems, we want to make sure to not confuse the phrase sampling distribution with distribution of the sample. The sampling distribution is the third level, right? That's where we're seeing how the means or proportions from sample to sample are varying. The distribution of the sample means at the second level, how is the sample itself distributed? That refers more to the standard deviation S in the sample for numerical data. All right, so we've got our summary. I think we've kind of beat that into the ground. What we're going to do next is work just two problems. We usually do this as part of finishing off the notes. So these are the two first actual problems in your required practice packet. So I'm going to switch to the required practice packet. Actually, I think I can just do it right here. We're going to start with example A. So let me clone this page, and we'll solve both of these problems. Okay, I want to start with the numerical one. Okay, so this should be practice problem number 1 in your, actually, no, let's start with the other one. Let's start with this one. I want to start with the mean. So this is actually labeled practice problem number 1 in your required practice packet for 18. Okay, suppose that the mean adult weight is 175 pounds with a standard deviation of 125, okay, in some particular region of the country or world or something. Okay, an elevator in a building has a weight limit of 10 persons or 2,000 pounds. So you can put 10 people on it, but you don't want to exceed 2,000 pounds total. What's the probability that if I put 10 people on, that they will overload the weight limit? Okay, so how can we use the stuff from this part of the problem to realize this, right? Well, first thing we might ask ourselves is this a proportion problem or a mean problem? Right, so I've got some things here. They give me the word mean here, and this seems to be not about yes or no things, but about numbers. So this is definitely a means problem. It's important to ask yourself that question first so that you're dealing with the right set of formulas and conditions, okay? So since we're talking about numerical variables, we have means, okay? For me to analyze this, I'm going to want to figure out what the mean and the standard deviation are for the sampling distribution. So I want the mean of the means and the standard deviation of the means. And that means I'm going to be finding the probability. We'll talk about how to do the probability part first, but let's just talk first about the means, right? So if I had a let's look at the three levels. If I have my population level, which means I have people, and they have a mean of 175 pounds with a standard deviation of 25 pounds, and I take a sample of 10 of them at a time. So I'm going to take an n equals 10 sample here. And that means in that sample, I'm going to get 10 people at random chosen, and those 10 people will generate a mean, and there'll be a standard deviation in that sample as well, right? Okay, what I'm really interested in is if I take 10 people at a time, how much does this mean move around? What's its sampling? So if I go down here to the sampling distribution model level for the sample means, right, that's going to have each X bar for a bunch of different cases. If I took 10 people at a time and weighed them and then found their average weight, what would that look like? Well, we would have a mean of weights of the means and a standard deviation of the means. So let's actually compute those values, because the mean of the means, we have a formula now that says that that's aligned to the mean of the population. So if the population averages 175, then the average weight per person in our group of 10 would be 175 pounds. Okay, the standard deviations down here, if I look at individual people, they vary with a standard deviation of 25 pounds, so quite a bit of variation. But if I take 10 people at a time and then average them, then I have to use this formula, sigma over the square root of n. So 25 divided by the square root of 10, which turns out to be 7.906 pounds. That's how the means are going to vary. So let me be real explicit here. I'll use black here. I'm going to make a new distribution here, and this is going to be the average weight per person in a sample of 10 people. Okay, so that's going to have an average weight of 175 pounds, but the standard deviation is not going to be 25. It's going to be narrower. I should have drawn it narrower. It's only 7.906 pounds on either side here. Okay, so if I take 10 people, add up their weight, divide by 10, and find the average, the mean weight, that's how much variation it has, less than this. Okay, so now we want to use this sampling distribution model to solve this probability problem. What's the probability that the 10 people will overlay the weight limit? Okay, so if the weight limit is 2,000 pounds, but there's 10 people, then that means we would have to have a group of people who average 200 pounds per person, right? So that limit there is a boundary value on this, right? If I go out here, somewhere out here above 175 is 200 pounds per person. And I could figure out how likely that is to happen. Overload would be if the average weight per person is more than 200 pounds. All right. And since I know this is a normal distribution, well, I don't know that yet because I haven't checked my conditions. Okay, to use this sampling distribution, we have to meet the conditions. So at some point in the problem, we need to check the conditions. Let me do that right now. What are the conditions for using means? Well, the first is, for this to be normal, we have to have a big enough sample size, and it has to be that n is at least 30, or we have to sample from a normal distribution. Okay, so do we have n equals 30? No, this is not met because we only have a sample of 10. N is only 10, but we know that weights of people are usually normally distributed. That's a normal kind of thing, right? So we're going to assume this is true. This is true because we're sampling from a normal distribution. So that condition is met, not because the sample size is big enough, but because we know that weights of people tend to be normally distributed. Okay, the second criteria is you have to have an SRS, a simple random sample. Now that we don't really know. This is a question. Are the 10 people in our sample typical of the people in the population? In this case, we're just going to assume that the sample is representative. And if we're assuming that, we will always want to state that we're assuming that. So we're checking conditions here. We should give a reason why we think that condition is met. The last one is that you want to sample less than 10% of the population. So that would mean that our sample of 10 is less than 10% of all people. And that's definitely true. So that's met. So we've met the three conditions, and that means it's okay to use this distribution over here to do probability calculations. So now we're just going to find the probability of having the average weight per person be at least 200 pounds. So the probability that the average weight is at least 200 pounds is normal CDF from 200 as our lower boundary labeled to infinity as the upper, with a standard deviation, or with a mean of 175 and a standard deviation of 7.906. Okay, and at this point we know how to get that in a calculator. We get that it's 7.83 E negative 04, which means 7.8 times 10 to the negative fourth, which is the same as 0.00078. So that's extremely unlikely. What this is saying is that if you have a 2,000-pound weight limit and people really weigh this much on average, right, then that means there's way less than 0.1% of overloading the elevator, even if 10 people get on it. Okay, but you see how everything ended up being about average per person, because that's what we're computing here. We're finding means. It's the average, and then we use the sampling distribution to show how we expect that to vary. So try that problem again. You're going to have to look at the blank problem and try it again on your own just to get that. But if you fully understand that, then you're good to go on chapter 18. This is the kind of way we use a sampling distribution. Okay, and then to finish this presentation, I just want to do the same thing except for a yes or no categorical variable. So let's look at the next one that's in your practice packet. It's labeled number 2. Okay, and for this one, it says, suppose that about 13% of the population is left-handed. Okay, a 200-seat school auditorium has been built with 15 lefty seats that have built-in desks on the left rather than the right. In a class of 90 students, what's the probability that there will not be enough seats for the left-handed seats? Okay, for the left-handed students. So the first thing we would ask ourselves is this a proportion or is this a mean problem? Okay, in this case, we're talking about a percentage. That's a pretty big clue that we're talking about proportion. And we have yes is left-handed, and then right is just right-handed, right? So this is definitely a proportions problem, okay? And that means that we're going to be trying to find the mean of the proportions and the standard deviation of the portions to get the normal curve for that, okay? All right, and we will deal with the probability part at the end. Right now, let's go ahead and check the conditions right now before we go any further. So what are the conditions for a to do an analysis based on the sampling distribution for proportions? Well, the first thing is you have to have a big enough sample, and that's that NP has to be at least 10 and NQ has to be at least 10. So the N here would be what? So this is a little tricky, right? We have a number of numbers here that we might think is N. It's not the 200 seats. That's kind of a red herring. It's the fact that the percentage here is about people, right? This P, this 13% is the P. I'm going to write it as a decimal, 0.13. That's the percentage chance of yes in the population, okay? So I'm not going to do the whole 3-level thing. I'm just going to show what I would actually write. I would identify that this 13% is P. Then I would go, this is a population of what? This is a population of people. So that means when I take a sample, I'm taking a sample of people. And so that means this 90 right here is the N. So we're taking a sample of 90 people. Yes is that they're left-handed, and the probability of that happening is 0.13. So that means that NP in this case is 90 people times 0.13, and that turns out to be 11.7, and that is greater than 10, so that's good. And NQ would be 90 times the other 1 minus 0.3, so the other 87%. That's the Q. And that turns out to be the other 78.3 people. So that means that the sample size is big enough for us to assume that this is a normal approximation to binomial, okay? The other thing is we have to be sampling less than 10% of the population. So this sample of 90, is that less than 10% of all students? Definitely true. So this is met, this is met. And then the last thing is we have to have a simple random sample. Is this sample of 90 students representative of all students where we calculated this 13% of the population? We're going to say yes, because we're going to assume that these 90 are representative of typical people. Okay, so we've met the 3 conditions, and that means it's okay for us to draw a sampling distribution, okay? But this is going to now be well, if I take my proportion, how much is that expected to vary around? Okay, so the mean of this sampling distribution model for sample proportions will align itself with the population's value of 13. So this will have 13% left-handed people in any sample of people, okay, on average. But the standard deviation is given by the square root of PQ over N, right? So if I calculate that, the P is 0.13, the Q is 0.87, 1 minus P, and then the sample size was 90. And that turned out to be equal to 0.0354. 0.0354. So what that's saying is if you take different classes of 90 people and you say, well, what percentage of the people are left-handed? Usually it'll be around 13% of the class is left-handed because 13% of all people are left-handed, but it's going to vary from class to class. The standard deviation of that variation from class to class is going to be 0.035, so about 3.5% standard deviation, okay? Now let's go to the probability problem. The probability problem is asking us what's the probability that will not be enough seats, not enough left-handed seats. Okay, so well, if we're talking about we have only 15 seats in the auditorium that are left-handed, and we have 90 students in a class, then that means the boundary when we would stop. The last time we would have enough people would be if there were 15 left-handed people out of 90. So I want to convert that into a proportion, like a p hat for a sample for a class. So if I had 15 out of 90, that would mean that 16.67% of the class was left-handed, right? So if 16.67%, then we'll have 15, and that means that we'll have enough seats, right? So for us not to have enough seats, it would mean that we're finding the probability that the p hat for any particular class is greater than that 16.67%. Right, so that means that somewhere over here above 13%, there's a boundary value where this particular class is something above 0.1667, and that means the probability we can find with our normal CDF function, because we've gone through the conditions to say that this is a normal shape. Normal CDF from 0.1667 to infinity. If the mean is 0.13 and the standard deviation is 0.0354, labeled lower, upper, mean, standard deviation. So if you plug that in a calculator, you end up getting 0.1479. So what that's saying is there's about a 15% chance that any particular class of 90 students will have too many left-handed students, too high a percentage of left-handed students, so that the desks would cover them. Now, those are not easy problems. Some problems will be easier than that, but I wanted to start with two pretty challenging ones so you can kind of see the range of how these are used. All right, so that concludes the notes for chapter 18. That's everything we're covering. The rest of this is just practice. It takes practice to see how to find the values to check conditions, to know whether you're dealing with means and proportions. But give the problems in your practice packet a try, and maybe start with the ones in the back, the practice quiz.